So now we know about uniform circular motion based on centripetal force. It's going to be motion that has a tangential velocity and an acceleration pulling it towards the center of a radius. But what about motion that is circular but not uniform? I mean, look at the path that this might follow. That is a crazy circular shape. We can't really investigate that with uniform circular motion, and we can't investigate that with kinematics either. Those curves, we don't have a way to deal with those curves, man. We call this angular motion. And in this context, we might have some kind of velocity that is changing this way. We might have a velocity that is in flux that might have some acceleration that's changing. And so to investigate this, we need a different set of variables. Fortunately, it's extremely straightforward. Whenever we talk about angular motion, we basically just go, hey, you remember all of that stuff we did at kinematics? Let's just make that angular kinematics by just thinking of everything in terms of angles, rotation. And so we really take our same variables that we used in kinematics and we just adjust them slightly. We just have angular versions of all of these. And so let's learn these. First off, we have x, our displacement. Angular displacement will be tracked using theta, which is normally what we would use to signify an angle. So that's going to take a little bit of getting used to. So an angle could have been represented by theta, but if we have an arc that we trace, we could also say that that from here to here traced theta. This gets measured in a concept called radians. Radians are incredibly useful when we're doing circular motion and angular motion because they allow us to get rid of the meter and judge things in a circle completely independent of the size of that circle. And we'll get into how radians work in just a second, but they're really just a way of thinking of going around a circle. And so let's look at our other variables before we actually talk more about what a radian is. Velocity, we're going to represent using the Greek letter omega, which looks like just a kind of curly W. And so we've got omega naught and we've got omega. That is going to be measured in radians per second. Acceleration, we measure using alpha, which we just trace like that. And we measure that in radians per second squared. Time is going to be the same whether we're moving linearly or angularly. So time just equals time. We don't have to change time at all. It's just seconds. So the only changes are our vectors. Our vectors get a circular version. And so how do we go from a displacement to theta? How do we go from meters to radians? Well, it's actually very simple. X will equal theta times the radius of a circle. Velocity will equal omega times the radius of a circle. And acceleration will equal alpha, you guessed it, times the radius of a circle. So if we have a circle here, let's talk about what a radian actually is now. You might have heard this in math class, but in case you haven't, let's talk about it. When we have a circle, we could track going around that circle in degrees. We could call this 0 degrees. We could call this 90 degrees. We could call this 180 degrees. And we could call this 360 degrees. And that has its uses, mostly that it's traditional, and we've used it plenty of times before, but it isn't very clean mathematically. And so if I've got this circle is going to have a certain radius, right? And it's going to have a certain circumference going around that. Well, that circumference will equal 2 pi r. 2 times pi times the radius. And so we make radians a very convenient way of getting rid of this r and this c so that we don't have to track things in meters. And we say there are 2 pi radians around a circle. And so if I go to 180 degrees, I say I've moved pi radians around that circle. If I go all the way around the circle, I have moved 2 pi radians around that circle. If I've gone 90 degrees would just be pi over 2. And 360 degrees would be 3 pi over 2. 3 over 2 pi. Really 1.5 pi. So when we track in radians, the usefulness is that this radius, suddenly the size of that doesn't matter. This radius could be 5 meters. It could be 0.05 meters. If I go around this circle in 1 second, if I go 2 pi radians in 1 second, I've moved 2 pi radians per second. And it doesn't matter what the radius of that circle is. This allows me to have a really clean and concise way of doing math around a circle without having to worry about without having to change it, without having to calculate a circumference every single time I want to do that. It also gives me a very easy way to convert back and forth from linear to angular kinematics. Because if I can figure out how many radians I've traveled, I can just multiply that by the radius of the circle and it'll tell me how many meters I've traveled. So if I'm moving on a bike and I go, hey, I move, let's say I make 10 full rotations of the wheel, well, each rotation is just going to be 2 pi radians. And so I could say, well, what's the radius of the wheel? Well, the radius of the wheel, let's just say it's 1 meter. Well, then I've traveled 10 times 2 pi meters. It's actually a pretty easy calculation. It's a pretty straightforward conversion once you get used to it. So these are our variables. These are our equations for converting back and forth between those variables. And these equations should make intuitive sense. Let's look at the units here. Let's look at the units for the velocity, the angular velocity. Omega is going to be tracked in radians per second. Now, if I wanted to convert that into meters, well, I would just multiply that by a meter. And that meter that I'm going to get from a radius. And when I do that, radians, which is really not a unit at all, it's just a way of thinking about a unit. We could really say that that doesn't quite exist. It's just a 1 there, 1 over seconds, times a meter. Well, that's going to give me meters per second, which would be a velocity. So that works out nice and easily like that. So then, if those are our variables, what do our angular kinematic equations look like? Well, that's what makes this so convenient. That's why we use radians, because our equations don't change. We just adjust the variables. And so now I'm going to use theta instead of x, and I'm going to use omega naught instead of v naught, then 1/2, and then alpha instead of a. And my displacement equation is the same format with just slightly different variables. With a little bit of practice, that'll look exactly the same. And there's my acceleration equation, just omegas instead of v's and alpha instead of a. And then I can even do the combined equation. Omega squared equals omega naught squared plus 2 alpha times delta theta. Nice. So these are basically exactly the same. What about the centripetal force equation? Remember, that was F equals mv squared over r. Well, we could say that v equals omega r. So we could substitute this in. So we could say m and then omega r squared over r. That would be m omega squared over r. R cancels out the square, and we get m omega squared times r. That'll come in handy too, because we'll be able to calculate things with centripetal force and centripetal motion while we're still in radians. We don't actually have to move back to our kinematics, our linear kinematics, before we do that. So we've got a centripetal version of this as well. And then the one last thing we need to take note of is when we're moving in angular motion, like what we're going to look at in just a couple of videos with satellite motion, when we're going around in that circle, there are two concepts we can think of when moving around that. One is, how much time does it take to complete one full rotation? One rotation. If I think about that concept, I get this concept of a period. We call it a period of rotation. And I represent that with a capital t. So period is going to be how many seconds in one rotation. But I can also ask, how many rotations in 1 second? Now this is going to be really useful for when we have things that are moving very quickly, like sound waves, which vibrate back and forth. When I pluck a guitar string, it's going to move back and forth. And if I had to say how many seconds between each oscillation of that sound wave, it would be a very small number. So we can say how many seconds or how many cycles per second. And when we do that, we get a concept called frequency. And frequency and period are just inverses of one another. So period is equal to 1 over frequency. We track period in seconds, and we track frequency in 1 over seconds. Those units should make sense. So it's really seconds for period and 1 over seconds for frequency. But we also have a special name for that. We call that hertz, and we measure it with Hz. We designate it with Hz. So then, what is the relationship between these, all of these, and these angular kinematics? Well, if we think of it this way, how many radians are in one full circle? 2 pi, right? So 2 pi radians. And then what are the units for a omega? It's going to be radians per second. Well, to get rid of the radians, I can just divide by 2 pi, right? Then I need the seconds on top, so I actually need to go 2 pi times seconds over radians, which that would just be 2 pi divided by omega. So that didn't make sense. That's okay. Just try and work the mathematics of that out on your own. But these values are all going to be related to each other like this. And this will come in very handy when we look at satellite motion. It'll also come in handy in waveform. So if you ever study anything a little more advanced, this relationship becomes extremely important when looking at how energy and waves move back and forth. So let's take some time and practice using these angular kinematic equations, though they should be pretty straightforward because they're going to follow the same form and function that we've already gotten used to in kinematics. So this should be kind of review. And then after that, we're going to take a look at satellite motion. We're going to put all of this together.